In this video, I will explain Ableton Live's Spectrum device. Spectrum analyzers are great tools to have in any type of audio production. Ableton has a spectrum analyzer called Spectrum. Spectrum analyzes the frequency content of incoming audio. Spectrum does not affect the sound of the incoming audio. To understand spectrum, one needs to understand frequency. Frequency is what sound is made of. Sound is vibrations that move through the air. If a force, say a speaker, vibrates the air molecules at a certain rate, our ears can interpret those vibrations as sound. For those vibrations, or we could say oscillations, to be called sound, they must be oscillating at a rate of 20 cycles per second to 20,000 cycles per second, or we say 20 hertz to 20,000 hertz. Hertz measures cycles per second. Hertz is how we measure frequency. Hz for hertz and kHz for kilohertz. Kilo meaning 1,000. 20 hertz to 20,000 hertz is the frequency range of human hearing or sound. This range of frequencies is what Spectrum analyzes. I will load Spectrum onto an audio track where I have audio samples loaded in Ableton's session view. If I play the audio of one of the samples, you should see something happening in this window here. If you want to see this window larger, you can select this triangle tab or double-click in the window. Sound is made of frequencies. Different sounds contain different sets of frequencies. A sound's frequency content can change over time. What we are looking at in this window is the frequency spectrum of sound that is happening at a particular point in a sound that is playing into Spectrum. You can see in the window that there are vertical lines and horizontal lines. These lines represent sound's frequencies and the amplitude of those frequencies. Notice the numbers on the left. Those numbers represent amplitude. Notice 100, 1K, and 10K at the top of the window. Those numbers represent frequency. The moving blue line represents what frequencies are happening in a particular sound. We divide the frequency spectrum into low frequencies, the low numbers, mid-range frequencies, the middle numbers, and high frequencies, the high numbers. Low frequencies on the left, and high frequencies on the right. Notice on the left the vertical line here that represents 20 hertz. This is the low side of human hearing. Notice on the right side this line here that represents 20 kilohertz. This is the high side of human hearing. Spectrum does analyze some frequencies outside of the human hearing range, above and below. As I hover the cursor in the window, pay attention to the lower left corner of the window in the blue box. You will see frequency numbers changing in the blue box as I move the cursor from left to right. The frequency numbers are measured in hertz. Where I am hovering the cursor in the window indicates what frequency we are analyzing at that point in Spectrum's window. Low frequencies are on the left. Mids, or mid-range frequencies, are in the middle. And high frequencies are on the right. What we are looking at in the window from top to bottom is what amplitude the frequencies are happening at. Amplitude is how quiet or loud we perceive a sound. We measure amplitude in decibels, dB for short. Notice in the blue box in the lower left corner of the window, when I move the cursor from top to bottom, we can see the decibel numbers changing. Where I am hovering the cursor in the window indicates the decibel of the frequency I'm hovering at in Spectrum's window. Notice when I move the cursor in the window, the frequency and the decibel numbers are changing at the same time. Where I'm hovering the cursor in the window will tell me the frequency as well as the amplitude in decibels of that frequency. The ghostly blue line in the background indicates the maximum accumulated amplitudes of the frequencies in a sound. Notice that when I stop the audio, the line remains. This line will give an indication of the maximum accumulated amplitudes of the frequencies in the sound that you were playing into Spectrum. You can toggle this line off and on here where it says max. You may wish to view the frequency content as discrete bins rather than as a line. You can toggle this here. You can choose between line and bins. As I change the volume of the audio going into Spectrum, notice the decibels and the lines that represent the decibels changing in the background of Spectrum's window. Notice that 0 dB is currently not showing on the left. If I raise the level of the audio enough to reach 0 dB, then the 0 dB line will appear. Notice that when I stop the audio, the dB lines and numbers changing. This compression and decompression behavior of the decibels window display values and lines is because I have Spectrum set to auto. With auto selected, the display graph automatically scales itself based on the incoming audio level. You can change this automatic scaling behavior here. Toggle from auto to range. With range selected, you can set the display's dB values manually here. You can set the maximum displayed amplitude values on the left and minimum display values on the right. If I hover the cursor over the dB values on the left of the window, a magnifying glass appears. With this, you can drag vertically to scroll the values, and you can drag horizontally to zoom. Or you can do it manually. I'd like to set mine to match the track's meter, 0 dB for maximum and -60 dB for minimum. You may ask, why are the decibels measured with negative numbers? The measurement of decibels Spectrum uses is dBFS, or decibels full scale. dBFS is what digital audio software such as Ableton Live uses to measure decibels. If we look at a track's meter in Ableton's session view, we can see that 0 dB is at the top of the meter and -60 is at the bottom. With dBFS, if your audio level goes over 0 dB, you may distort your audio. I like to set Spectrum's display to match how the track's meter is showing decibels, showing 0 dB at the top and -60 dB at the bottom. With this setting, the values in the window match the values on the track meter. With this setting, it also minimizes the displayed frequency content in the window that exists below an audible level. We can't hear this content here below -60 dB. All this information that is happening here is below -60. I don't have to see this in the window if I don't want to. As I play this sample of a synthesizer sound, I can analyze the frequency content. If I hover in the window over this frequency here, I can see in the lower left of the window that it is right around 65 Hz. If I hover over this frequency in the window, I can see that it is right around 130 hertz, a doubling or twice that of the first frequency. You may have noticed in the blue box in the lower left displaying frequency and the amplitude of that frequency that it also displays what note that frequency is. Every musical note has certain frequencies that relate to that note. The letter indicates what note it is, and the number next to the letter indicates the octave range of that note. If I play the sound of the synth again, and I hover over the same two frequencies from before, we can see that the first one is note C1, and the second one is note C2. If I switch the window display from log to semitone here, ST is for semitones. Spectrum's window display will now show the window scaled in semitones, in other words, notes. We can see the C octaves displayed at the top of the window. The lines between each octave represent the semitones between each octave, in other words, the notes from C to C. I will load an Ableton Live instrument called Operator onto a track. Then I will load Spectrum onto that same track. I will set my display to range and set the display view of the window manually. I will also turn off the max line and set the display to show semitones. If I play all the semitones or notes between two C notes an octave apart, we can see that indicated on the graph by the activity in the window. We can see the notes I am playing and which octave range it is. If I pay attention to the blue box in the lower left, or go between the semitones view and the logarithmic view, we can see which notes relate to what frequencies. I can see that this C note is right around 65 Hz. When I loaded Operator onto a track, it was defaulted to play only single frequencies. Notes played with different sounds or other instruments are not made up of just single frequencies. I will change the sound of Operator. I will select this waveform. We can see in Spectrum that this sound contains more than just one frequency, indicated in Spectrum's window display. And when I play different notes, those frequencies shift in the spectrum according to the note played. Usually the lowest frequency in a pitch sound is the note being played. So far we have been viewing the frequency display of Spectrum logarithmically. The window display is scaled this way with log selected. What does this mean? Humans hear pitch exponentially. What does this mean? I will switch Spectrum's display to semitones. If I play the notes of different C octaves, we can see what note I'm playing and which octave I am playing in. If I switch to log and play the octaves again and pay attention to the frequency of those notes, we can see that between two octaves is a doubling or halving of the frequency, depending on if you are going up an octave or down an octave. That means there is progressively twice as many frequencies in each octave above the next. If I play this G note, we can see in the lower left window in the blue box that it is right around 100 Hz. If I play the next G note an octave above, we can see that its frequency is right around 200 Hz, a doubling of 100 Hz. If I play the next G an octave above that, we can see that its frequency is right around 400 Hz, a doubling of 200 Hz. And the next G up is 800 Hz, a doubling of 400 Hz, and so on. If we graph frequency in octaves, we can see that it graphs on a curve. This is exponential. Logarithmic is the inverse of exponential. If we look at the graph in the window for the semitones display, each space for each note between each octave is equal in size in the display. If we were to scale this graph linearly, that is, in a linear way, the space between each octave would progressively need to double in size because it would have to display twice as many frequencies in each octave range above the next. This would take a lot of space in the window display. This is what the linear display shows. We can change this view here and toggle between log and linear by selecting LIN for linear. If I play the same synth sound from before and switch the display to LIM for linear display, we can now see that most of the displayed frequencies are jumbled up on the left side of the window. This is because we are scaling the window graph in a linear way. With this view, we can get a much more detailed view of the higher frequencies, but the lower frequencies have less space to display those frequencies. To display the frequency content in a way in which our ears and eyes can visualize, we use the log setting. We use the logarithmic setting to scale our view in a more usable way for frequency and pitch. With the logarithmic scaling, we can visually see all the frequency ranges in a sound more equally. We hear the pitch from octave to octave in a linear way to our brain's interpretation, even though each octave contains twice as many frequencies. In the same way, this is why the semitone scaling is used for pitch and notes. Logarithmic and semitone settings are actually the same scaling, but simply switch the legending at the top of the display between hertz and note names. Between these two displays, we can see how pitch and frequency relate across the entire spectrum of sound. You may be analyzing the frequency content of a stereo sound. Stereo sounds will usually have frequency information that is different between the left and the right. That is, the frequency in a sound happens differently between the left and the right speaker. With Spectrum, you can analyze the left or the right independently by selecting L for left or R for right. If you select both L and R, Spectrum will display the combined frequency information of both the left and the right channels. Spectrum's last three settings, block, refresh, and average, have to do with the way Spectrum processes digital information. The block chooser selects the number of samples that will be analyzed in each measurement. Samples are the ones and zeros, the binary information of our digital audio running through our computers. Higher values result in better accuracy, but at the expense of increased CPU load. The refresh slider determines how often Spectrum should perform an analysis of the frequency content. That is, how often it is analyzing the incoming audio. As with the block parameter, this allows for a trade-off between accuracy and CPU load. A fast response time is more accurate, but also more CPU intensive. The average slider allows you to specify how many blocks of samples will be averaged for each update of the display. That is how often it will update the Windows frequency display in real time. With a setting of 1, each block is shown. This results in much more activity in the display, which can be useful for finding the spectrum of short peaks, such as drum sounds. As you increase the average value, the display updates more smoothly, providing an average of the frequency spectrum over time. This is more consistent with the way we actually hear. With this, we can see the line is not moving as quickly.